In this video, which will be the 5th video in our module on graphs, we'll introduce traversals, and in particular, Eulerian and Hamiltonian graphs. So the subject of graph traversals has a long history, dating back to the 18th century Swiss mathematician Leonhard Euler, who worked on the Königsberg bridge problem. So here, in figure 1.1, you can see the left picture is a 18th century map of the city of Königsberg. And that map is translated on the right into an undirected graph. What the green oval shapes in the map represent are bridges from you can see there are 4 land masses. So this is B, C, D, and A. And these appear on the graph as the vertices, whereas the edges represent the bridges across the river. So the legend of the problem states that the citizens of the city were searching for a walking tour that would pass over each bridge exactly once. And no one could design a tour no matter how hard they tried. So Euler eventually studied this problem and he proved that such a tour was not possible. So here is the theorem as it applies to the Königsberg bridge problem. Euler's theorem states that no walking tour of Königsberg could be designed so that each bridge was used exactly once. And then the proof is discussed here. The map, as we saw above, could be represented as an undirected multigraph. The 4 land masses are the vertices, and each edge represents a bridge. The desired tour we can then interpret as a path that uses each edge once and only once. Since the path could start and end at 2 different vertices, then there will be 2 remaining vertices that must be the intermediate vertices in the path. So if X is an intermediate vertex, then every time that you visit it, you must use 2 of its incident edges, 1 to enter and 1 to exit. Therefore, there must be an even number of edges connecting X to the other vertices. But every vertex in the Königsberg graph has an odd number of edges, hence no tour of the desired type is possible. And he stated this theorem in more generality, which we'll see in just a moment. But first, we'll have the definition of an Eulerian path named after the mathematician Euler. An Eulerian path through a graph is a path whose edge list contains each edge of the graph exactly once. If the path is a circuit, then it is called an Eulerian circuit. An Eulerian graph is a graph that possesses an Eulerian path. So the example here is an Eulerian graph. Without tracing any paths in figure 1.5, we could be sure that the graph has an Eulerian circuit because all of the vertices have even degree. And so that will bring us to Euler's theorem. But let's just do a quick examination of this graph. If we chose a random vertex on the graph and counted the number of edges coming in or out of it, we would see that each vertex does have an even degree. And that is all we have to confirm in order to say that this must have an Eulerian circuit. So Euler's theorem in general says that an undirected graph is Eulerian if and only if it is connected and has either 0 or 2 vertices with an odd degree. So of course it must first be connected. That's seemingly trivial, but it's an important thing. We have to state that the graph must be connected and either have 0 vertices with odd degree or 2 vertices with odd degree. Furthermore, we can say that if the graph has 0 vertices with odd degree, then the graph will not only have an Eulerian path, it will have an Eulerian circuit. So it can be proven by induction on the number of vertices in an undirected graph, that the number of vertices that have odd degree must be even. So that can be proven by induction. We're going to skip the details of that proof. And the necessity of having either 0 or 2 vertices should be clear from the discussion above about the Königsberg bridge problem. So we'll concentrate on proving the sufficiency of this. Let's let K be the number of vertices with odd degree. This proof will be divided into 2 phases, and in each phase we'll discuss the case for 0 vertices with odd degree or 2 vertices with odd degree. These are our 2 separate cases. So first, if the graph has 0 vertices of odd degree, then we can start at any vertex and give it a name, V0, and then travel along any path, making sure that we don't use any edge twice. Since each vertex has an even degree, the path can always be continued past each vertex that you reach, except V0. So when you get back to V0, you stop, and you'll have a circuit including V0. This is what we do if K is equal to 0. On the other hand, if the number of odd vertices, or vertices of odd degree, is 2, then we'll let V0 be either one of the vertices of odd degree. And we'll trace any path starting at that vertex, using up edges until we can go no further, as in the K equal to 0 case. But this time, the path that we obtain must end at the other vertex of odd degree. So that other vertex of odd degree will be called V1. And this is the end of phase 1. So at the end of phase 1, we will have an initial path that may or may not be Eulerian. If it's Eulerian, then we're done. But if it's not Eulerian, then there's a phase 2, which we'll discuss in just a moment. But we want to note that in phase 2, the number of edges that are unused will decrease. And we can keep repeating phase 2, and in each successive application of phase 2, the number of unused edges will decrease. So we can conclude that the Eulerian path must be obtained within a finite number of steps because there are a finite number of edges to start with. So what is phase 2? Well, remember, we've already constructed a path, either a circuit if we had no vertices of odd degree, or a path from V0 to V1 if we had 2 vertices of odd degree. So we'll refer to the path that we've already created as the current path. Let capital V be the vertices of the graph, capital E the edges, and capital E sub U will be the edges that have been used in the current path. Now we'll consider the graph G prime, where we use the same vertex set, but now we're using E minus EU, so the set of edges that have not been used in the current path. Note that every vertex in G prime has an even degree. Select any edge, E, from G prime. Let V sub A and V sub B be the vertices that E connects. Trace a new path starting at V sub A, whose first edge is E. We can be sure that at least one vertex of the new path is also in the current path since the graph is connected. Starting at V sub A, there exists a path in the original graph to any vertex in the current path. At some point along this path, we can consider the start of the new path, which will have intersected the current path. Since the degree of each vertex in the new graph G prime is even, any path that we start at this vertex V sub A can be continued until it is a circuit. Now we will simply augment the current path with this circuit. As we travel along the current path, the first time that we intersect the new path, we will travel along it, as we can see in the figure below. Once we complete the circuit that is the new path, we resume the traversal of the current path. So I know that was a lot. If you need to pause the video and read back through that chunk of text one more time to understand what's going on, please do so. But basically, here we are traveling along our path from V0. Eventually we're going to get to where the graph intersects, or the path intersects, this new circuit. And when we do that, we're just going to go around the circuit and then continue on our path. That's essentially what we're saying. So we add this circuit in to our path. That's called augmenting the path. So you can see current path, and new current path in the path augmentation plan. So if the result of this application of phase 2 is an Eulerian path, then we are finished. Otherwise, we continue repeating this phase of adding in these circuits until we use up all of the edges, and then what results must be an Eulerian path. So some examples here of Eulerian graphs. We've seen this notation in a previous lecture that capital K sub n is the complete undirected graph on n vertices. So it turns out that k sub 2 and k sub 3, k sub 5, and all of the higher odd numbers of vertices, these are all Eulerian graphs. So the graph k sub 2 is Eulerian, k sub 3, k sub 5, k sub 7, and so on. And the way that they denote this is k sub 2n plus 1, n starts at 1. So all of these graphs are Eulerian. However, if it's a complete graph on an even number of vertices, it's not Eulerian with the exception of 2. So we've posed the question about finding a path that uses each edge exactly once. A next natural question to ask, or problem to tackle, might be the existence of a path that uses each vertex exactly once. So this is exactly the problem that was studied by a 19th century Irish mathematician named Sir William Rowan Hamilton. And just a fun side note here, it states he is honored, or he's credited with discovering the quaternions, if you're familiar with the quaternions, and the Irish government honored him with a postage stamp. And on the postage stamp you have I squared equal to j squared equal to k squared equal to -1. So that's just a fun little piece of math history. This same mathematician who discovered the quaternions studied this problem about graphs, and the idea of a Hamiltonian path or a Hamiltonian graph is named after him. So a Hamiltonian path through a graph is a path whose vertex list contains each vertex of the graph exactly once, except if the path is a circuit, in which case the initial vertex appears a second time as the terminal vertex. If the path is a circuit, then it's called a Hamiltonian circuit. A Hamiltonian graph is a graph that possesses a Hamiltonian path. So on the next page, we'll see the original graph that Hamilton studied. And originally, he posed this in a magazine or other publication as a puzzle called Around the World, where readers were encouraged to plan a travel through each of the cities of the world. And the challenge, of course, was to use each vertex exactly once. So this graph is also referred to as a dodecahedron graph because the vertices correspond with the corners of the dodecahedron, and the edges are the edges of the solid that connect the corners. So here's that graph that Hamilton first studied, and on the left you can see the dodecahedron that it corresponds to. Unfortunately, a simple condition does not exist that characterizes a Hamiltonian graph. An obvious necessary condition is that the graph be connected. However, with as few as 4 vertices, you can draw a connected, undirected graph, which is not Hamiltonian. So the search for a Hamiltonian path in a graph is typical of many simple-sounding problems in graph theory that have proven to in fact be very difficult to solve. Although there are simple algorithms for conducting such a search, they are impractical for large problems because they take a long time to complete, as the graph size increases. So currently every known algorithm to search for a Hamiltonian path takes exponential time to complete. And there's a bit more in this paragraph you can read about exponential time if you're interested. It is unproven but widely held belief that no faster algorithm exists to search for the Hamiltonian paths. So, in conclusion, the problem of determining whether a graph is Hamiltonian is theoretically possible. However, it has proven in practice to be mostly impossible, especially for large graphs. So, in the next section, we're going to introduce the traveling salesman problem, which, for the same reason, is thought to be practically impossible. Okay, let's look at one last application of these ideas before we do some exercises. So you have a definition here, 1.16, the definition of the n cube. So first we start with an n greater than or equal to 1, and we'll denote by capital B to the power n the set of strings of zeros and ones with length n. The n cube is the undirected graph with a vertex for each string in Bn, and an edge connecting each pair of strings that differ in exactly one position. The n cube is normally denoted q sub n. A Hamiltonian circuit of the n cube can be described recursively. The circuit itself is called the Gray code. It's not the only Hamiltonian circuit of this n cube, but it's the easiest to describe. And the standard way to write this circuit is as a column of strings where the last string is followed by the first string to complete the circuit. So here you see that the Gray code for the 1 cube is just 0 and 1, the column where the strings are just 0 and 1. Note that the edge between 0 and 1 is used twice in this circuit. That doesn't violate any rules for Hamiltonian circuits, but can only happen if the graph has 2 vertices. And here's how the Gray code is defined recursively. If we know the code for an n cube for some n greater than 1, then the next successive code is obtained by first listing gn with each string prefixed with 0, and then reversing the list of strings and listing them with each string prefixed with 1. So here's the recursive definition. Gn plus 1 is equal to prefix 0 and list all of the strings, and then prefix 1 and list all of the strings in reverse order. So what do we mean by that? Well, remember G1 was just 0 and 1. So in order to obtain G2, we have G1 here, and we prefix 0. Then we list G1 in reverse order, prefixed by 1. Now to obtain G3 from that, we have G2 here, and we just prefix zeros. And then in reverse order, we list G2 prefixed by 1. So in example 1.18, you can read about applications of this Gray code. One application is discussed in the introduction of the textbook. Another application is in statistical analysis when calculating the multiple correlation coefficient for a set. So you can read more about that here in the lecture note. Okay, so in the first exercise here, you can see that we have these 3 cartoon drawings, and the question asks which of the drawings can be drawn without removing your pencil from the paper and without drawing any line twice. So because it says without drawing any line twice, we're thinking of finding an Eulerian path or circuit through the graph. And without removing your pencil suggests that it should definitely be connected. So let's start labeling some vertices, we can think of where these lines intersect as vertices and try to determine the degree of some of these. So for example, the top of the left ear has degree 2. The top of the right ear also has degree 2. But here, where the ear meets the head, both of these have degree 3. As you can see, there are 3 edges coming in or out of this vertex. Similarly, I think that this vertex has degree, if I count, 1, 2, 3, 4, 5. This one here on the right side of the face. So I found at least 3 vertices with odd degree. So right away I could say, since there aren't 0 or 2, this graph does not have an Eulerian path, or this graph is not Eulerian. Now what about the next picture? I'm going to do the same thing. I'm going to label some vertices. So if I look at these ones around, I guess this is the mouth or the nose of this little guy, this appears to have degree 3, as does this one. But also here on the hat, these each have degree 3. And there are other vertices of even degree. But again, since I found more than 2 vertices of odd degree, if I'm thinking of this as a graph, I get to say the graph is not Eulerian. So I can't draw either of these first 2 graphs or cartoons without tracing over at least one edge more than once. Now what about this last one? Can draw in some vertices and try to assess their degree. So here at each of the ears, it looks like we have degree 4. Here's 1, 2, 3, 4 different edges. And here at the bottom, I have 1, 2, 3, 4, 5. Then I have, this is degree 4, and this appears to be degree 5. So I have 2 vertices of odd degree, which suggests that I should be able to find a Hamiltonian path, a path that uses each edge exactly once. And we know from our discussion above that this path is going to start at one of the vertices of odd degree and should end at the other vertex of odd degree. So let's try starting here in the center, right between the 2 eyes. So let's say I go around this loop. So I've exited the vertex and entered the vertex. So I need one more edge to leave the vertex and one more edge to come back. Finally, I need one more edge to leave the vertex. So I can go along this way, then down, and I haven't picked up my pen. Then I can go down and up and down and over, down and around the right ear, across the forehead, down and around the left ear, and back down. And I have ended up exactly here at the, so this red one is the terminal vertex and the green one is the initial vertex. All of the other vertices I passed through an even number of times to go in and out. So this graph has an Eulerian path. So we can draw it without picking up our pencil. And without tracing an edge more than one. Okay. The next exercise says consider the graphs below. Determine which of the graphs have an Eulerian path and find an Eulerian path for the graphs. So we're going to start in a similar fashion. We're just going to look at the degrees of the vertices and see if we have either 0 or 2 vertices of odd degree, then we should be able to find the Eulerian path. So looking at graph A, I'm going to start at vertex 15 in the top left. This has degree 2. Vertex 8 appears to have degree 4. Vertex 11 has degree 2. Vertex 2, it looks like has degree 3. And on the other side, in the same position, vertex 4 also has degree 3. So far I have 2 vertices of odd degree. If I encounter one more, then I would know that this doesn't have an Eulerian path. So vertex 9 has degree 2 as I'm making my way around, but vertex 12 appears to have degree 3. So as soon as I get there, I can stop and say, this graph definitely does not have an Eulerian path. What about graph B? Well, again, I'll start in the top left corner. This has degree 2. Vertex 9 has degree 3. Vertex 5 has degree 3. Vertex 1 has degree 2. Vertex 2 has degree 3. And again, I found more than 2 vertices of odd degree, so I can stop. Then, graph C, I'll start here at vertex 5 and count. This has degree 4. Vertex 4 has degree 4. Vertex 3 has degree 4. Vertex 2 has degree 4. And as I make my way around, it turns out that, in fact, all of these vertices have degree 4. So I should be able to find an Eulerian path in this graph. So I have already found one, and I'll write down the path in terms of the vertices that we pass through. First, we're going to go 1 to 7 to 3 to 9. So that's from 1 to 7, 7 to 3, 3 to 9. Then we'll go to 5, 11, 2, 6. So up to 5. And over to 11, then to 2, and from 2 to 6. Then I want to go to 10, 4, 8, 2. So I'm at 6. I go here to 10, from 10 to 4, from 4 to 8, and from 8 to 2. Then I'll go from 2 to 3, 3 to 12, 12 to 4, 4 to 11. So I'm here at 2. The last choice that I have is to take this path to vertex 3. Then from 3, my last available path or unused path is to vertex 12. From 12, I'll choose to go to 4. And from 4, my last choice is to go to 11. Let's see if I can get that back on track. From 12 to 4, from 4 to 11. All right, and then I'm going to go to 1, 12, 5, So from 11, my last choice is to go to 1. From 1, I'll go to 12. From 12, the last path or edge that I haven't traversed goes to 5. And now it looks like I've pretty much covered them all except for this exterior edge. So from 5, I can go to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10, and from 10, I'll end up back at 1 where I started. So this is in fact an Eulerian circuit because I had no vertices of odd degree. I could find such a circuit beginning and ending at the vertex 1. Now similarly in graph D, if I observe the degrees of the vertices, I'll find that vertex 4 has degree 2, vertex 11 has degree 4, vertex 12 has degree 2, then 4, then 2, then 4, 2, and 4, and then inside I have 2, 2, 2, and 2. So I should again be able to find an Eulerian path, and in fact, just from looking at it, it's pretty clear that there are a bunch of different ways we could do this. So I can go from 5 to 10, 10 to 11, 11 to 9, 9 to 8, 8 to 1, 1 to 2, 2 to 3, 3 to 5. So tracing out this entire inner circuit, and then keep going. Should have 3 there as well. Then I can keep going and do the outside circuit. And I could do it clockwise or counterclockwise if I wanted. 5 to 6, 6 to 2, 2 to 7, 7 to 8, 8 to 12, 12 to 11, 11 to 4, 4 to 5, for example. But there are many different choices I could have made. So this is also an Eulerian circuit. But as I say, I could have gone clockwise instead, or counterclockwise. I could start at a different vertex. I could start, say, maybe here at 8, and I could go around inside, and then maybe I could jump outside and do a couple here, then back inside, outside, outside, inside, and outside. That would also be, oh, gotta finish off here, inside. That would also be another Eulerian circuit. So there are lots of different choices we could make here. Okay, the next exercise says, under what conditions will a round-robin tournament graph be Eulerian? So it turns out that this is actually going to be pretty rare. There are certain conditions that will ensure that this is true, however. So a round-robin tournament graph is Eulerian if it has an odd number of vertices and each vertex, say these vertices are representing teams in a tournament competition, each vertex or team wins exactly as many times as it loses. Now this may not be the only instance, but this very specific set of conditions will ensure that the round-robin tournament graph is Eulerian. The next part of the exercise, it asks us to prove that every round-robin tournament graph is Hamiltonian. So this proof will require induction, which is a technique that we've seen in a couple of lectures before. If you have not had a course in mathematical proofs and you are not familiar with proof by induction, that's okay. You're not required to be able to do this kind of proof, but you should follow along with what I'm doing and try to understand the logic behind it. So the first thing that we do is we define a proposition. We'll say let P of n be the proposition that a round-robin tournament graph has a Hamiltonian path. This is what it means to call the graph Hamiltonian. So the round-robin tournament graph, and it's important that I say with n vertices because this is a proposition of n. So this is what I wish to prove is true for all n. And I'm going to start with the most basic case being the natural number 2. So I'm going to say P of 2 is obviously true. Why is it obviously true? Well, imagine that I have a graph, a round-robin tournament graph on 2 vertices. Then I would either have the first team beat the second team or the second team beat the first team. In either way, I clearly have a Hamiltonian path from one team to the other. So P2 is obviously true. The next thing we're going to do is we're going to assume that P of k is true for some natural number, k, greater than or equal to our base case 2. That is, we'll assume that a round-robin tournament graph on k vertices is Hamiltonian. Or we'll say has a Hamiltonian path. Same thing, but that's how we worded it before. Okay. Now, our general strategy, because all we really have to work with is this assumption, this inductive assumption about the case for k vertices. So what we're usually going to do is we're going to consider the next case. So consider a round-robin tournament graph with k plus 1 vertices. And we're going to try to somehow connect it back to the previous case so that we can use what we're assuming about k to establish this for k plus 1. So let's give this graph a name. The round-robin tournament graph with k plus 1 vertices, we're going to call it G. And let's choose any vertex in G and call it V naught. Or V sub 0. Then, if we consider the graph that we form from taking the set of vertices without V0 and removing from the set of edges the edges connecting to V0, we will have a round-robin tournament graph on k vertices. Round-robin. So, by assumption, we can find a Hamiltonian path. we're going to label the vertices along our Hamiltonian path to be V1, V2, up to Vk. Now, let's take small I in the set from 0 up to k to be the smallest, or rather the largest number in the set 0 up to k, such that for all natural numbers smaller, so for all j less than or equal to I, there is a directed edge initiating at v sub j and terminating at v sub 0. Then, if we consider the path v1, v2, up to v sub I, and then we throw in v0, and we have vi plus 1 up to vk, this path will be a Hamiltonian path in the graph G on k plus 1 vertices. So we've shown that the proposition is true for k plus 1. Thus, by the principle of mathematical induction, we've proven that it's true for all natural numbers greater than or equal to 2. So we'll say Pn is true for all n in script n greater than or equal to 2. And that completes the inductive proof that any round-robin tournament graph is a Hamiltonian graph. The last exercise that we have here in this lecture note is to write the Gray code for the 4 cube. So let's recall that the Gray code for the 1 cube was 0, 1. For the 2 cube, we had 0, 0, 0, 1, 1, 1, 1, 0. For the 3 cube, we had 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, and 1, 0, 0. So to form the code for the 4 cube, remember, we're going to write, first we just write the Gray code again in exactly the same order. And in front of each of those, we fix a 0. Then we go in reverse order, writing them down again. So 100, 101, 111, 110, 010, 011, 001, and 000. And in front of each of these, we fix a 1. Now if we count, and we've done this right, we should have 16 rows here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And this will be the column for the Gray code with all of the strings of length 4 of 0s and 1s. And that is the last exercise on this lecture note, so we'll conclude the video here, and we'll learn about graph optimization in the next video.